Hello everyone, I'm Benoît Freiche. I'm a PhD student at Clarysse in Lyon. And today I will speak about hierarchical manifold learning way of characterizing myocardial ischemia and reperfusion patterns. So we are in the context of acute myocardial infarction. So ischemia can lead to necrosis of the myocardial cells, which is called infarction. And when we cure infarction, we reperfuse the earth, sorry, and this reperfusion leads to a sudden surge of blood in area which were deprived of in oxygen, and it can lead to reperfusion injuries like microvascular obstruction (MVO), which is at interest today. So we aim at better understanding the underlying mechanisms of microvascular obstruction and other reperfusion injuries by characterizing reperfusion and ischemia patterns. To do so, we used the MIMI cohort, which is a set of late gadolinium enhancement magnetic resonance images of 123 patients with acute myocardial infarction, along with their segmentation in three classes, which are the healthy myocardium in blue, the infarction in yellow, and the microvascular obstruction MVO in dark red. First of all, we aligned all our data slice by slice in order to obtain a bit more than 1,700 2D slices of both the LDE images and their segmentations. If we look at two slices of patients in our database, here we can see that the segmentation patterns are quite similar, but the image appearance are really different. So it means that the image appearance is really rich, and it could be valuable for clinical analysis to better exploit the image directly the image appearance. But the problem is that in our context, MU is displayed as dark areas inside of brighter ones, and this dark color is the same as LC myocardium. So the algorithm can mistake between MVO and LC myocardium. Also, in MRI, we have some imaging artifacts. All of this leads to the fact that the image appearance is difficult, challenging to exploit. One way of exploiting this image appearance is by doing fusion. So fuse several descriptors. So here's the segmentation and the images. We have two ways of doing this, which are multiple kernel learning, which is an optimization process to find the best combination of several affinity matrices, and similarity network fusion, which is an iterative fusion process to obtain a fused similarity network. The problem of both of these methods is that they put all descriptors on the same level, but in our case, we have a clear hierarchy between the segmentation for one part and the images for second part. One of them is really easy to exploit, but is not really rich. But the second has really richer information, but is hard to exploit. So we decide to exploit these different modalities in a hierarchical framework. The first step is to build the embedding for the level 0, so the segmented images x0. So we build the embedding y0 corresponding. Then we fuse the information from the population x1 to obtain the level 1 of the hierarchy, which is our hierarchical embedding y1. To do so, we used the hierarchical cost function of Batia. Duchateau designed it for the multiscale image analysis of a single modality, where we do it for the hierarchical integration of two modalities. So if we look at, if we have a closer look of this equation, the y1 is the hierarchical embedding we are looking for. The first part of the equation is the spectral embedding for x1, which is basically using the affinity matrix of x1 to find the normalized graph Laplacian of this data. And we take the first few eigenvectors of this normalized graph Laplacian to build the embedding for x1. And the second part of the equation is the proximity between the levels 0 and 1. And both of these two parts of the equation are weighted by the parameter mu, which is between 0 and 1, and it balances the contribution of level 0 and level 1. The good thing about this hierarchical cost function is that we have an analytical solution, so the computation is fast and easy to implement. We designed two strategies to choose mu. First, we computed the distances between the child, so the images embedding, sorry, and the hierarchical embedding, and also the distances between the parents, the segmentation-based embedding, and our hierarchical embedding, and we choose the mu corresponding to an equal distance to the child and the parent. Within the same process for the energy corresponds to this equation. So we have the child part here and the parent part here, and we took the mu corresponding to equal energy between the child and the parent. So we display the results here. So in the left we have the embeddings corresponding to the level 0, so the segmentation, and in the right the embedding for the images. We displayed them into 3 different color scale. The first color corresponds to the quantity of infarct in the slices. So in red is the great quantity of infarct, and in blue really small infarct patterns. The second color corresponds to the MVO, and the purple dots are slices without any MVO pattern. And the third color scale is the intensity of the images. So when we display the embedding for both the energy method and the distance method, we obtain balanced contribution between the level 0 and the level 1. So we conserved the structure, the global structure of the level 0 embedding, but we have far more information about the images. Another way to look at this result is to look at the neighborhood consistency. So we take 2 patients here, and we look at the 4 closest neighbors in first the LGE images based embedding and the segmentation based embedding for the patient 2, and we look at the neighbors for the hierarchy. What we can see is for the patient 1, in the LGE images based embedding, the images are quite close, which is normal, but the segmentation, the 3rd and 4th segmentations are really different from the original segmentation pattern. In the hierarchy based embedding, we have really good, really corresponding images to the space, to the original images pattern of the patient. And it's the same for the segmentation. We have really good segmentation compared to the patient, the original patient. For the patient 2, the segmentation-based embedding have no coherence in terms of images, whereas the hierarchy-based embedding is images are really close to the original pattern, and the segmentation are good too in the hierarchy-based embedding. So as a conclusion, we exploited the magnetic resonance LGE appearance with a hierarchical dimensionality reduction framework for the descriptor fusions. We designed 2 strategies for the hyperparameter selection. And for the future, we would like to improve the metrics for the quality assessments of the embeddings, and also incorporate other modalities like T1 native and T2 stars. I thank my collaborators and funding agencies, and I thank you for your attention, and you feel free to ask any question.